Hello friends, in this video we shall learn row reduction and echelon forms of the matrix. This video refines the method of row reduction algorithm that will enable analyze any system of linear equations. By using only the first part of algorithm, we will be able to answer the fundamental existence and uniqueness questions posed. The algorithm applies to any matrix whether or not the matrix is viewed as an augmented matrix for the linear system. So, the first part of this section concerns an arbitrary rectangular matrix and begins by introducing two important classes of the matrices that include the triangular matrices. In the definitions that follows, a non-zero row or column in the matrix means a row or column that contains at least one non-zero entry. The leading entry of the row refers to the leftmost non-zero entry in a non-zero row. A rectangular matrix is in echelon form or row echelon form if it has the following three properties. First, all non-zero rows are above any rows of all zeros. That means the row containing all zero is at the bottom of the matrix. Second, each leading entry of a row is in column to the right of the leading entry of the row above it. That means leading entry means the first non-zero element in the row. Leading entry means first non-zero element in the row. That each leading entry of the row in a column to the right to the leading entry of the row above it. Third, all entries in the column below the leading entry are 0. If these three properties are satisfied by a matrix, then it is called as matrix in echelon form. We shall see again the definition of the matrix in echelon form. A rectangular matrix is in echelon form or row echelon form, both have same meaning, if it has the following three properties. First, all non-zero rows are above any rows of all zeros. That means row containing all element 0 is placed at the bottom of the matrix. Second property, each leading entry of the row is in column to the right of the leading entry of the row above it. All entries in the column below the leading entry are 0. That means नॉन-झिरो रो हे 0 रोच्या वरती असतात. नंतर खालच्या रोची रीडिंग एंट्री ही वरच्या रोच्या लीडिंग एंट्रीच्या कॉलमच्या उजव्या बाजूला असते. लीडिंग एलिमेंटच्या खालचे सगळे एलिमेंट त्या कॉलम मधले 0 असतात. If the matrix is echelon form satisfies the following additional conditions, then it is in reduced echelon form or reduced row echelon form. Fourth property, in addition to that above three properties, the leading entry in each non-zero row is 1. And fifth property, each leading one is the only non-zero entry in the column. That means column containing leading 1 has all other elements 0. If these five conditions are satisfied by the matrix, then it is called as reduced echelon form or reduced row echelon form matrix. The following matrices are in echelon form. The leading entries alpha may have any non-zero value. The star entries may have any value including zeros. This is a matrix in echelon form, and matrix in row echelon form is row reduced echelon form. That means this is a leading one and all other entries in that column are 0. Dear friends, if you are not subscribed the channel yet, subscribe it. We are going to upload all the videos on all the syllabus of matrix algebra required for F.Y.B.Sc computer science. Don't forget to press bell icon so that you can get updates of the channel. Friends, we are also providing the notes in a special group. We are also provide solutions of the examples in the exercise of the text given. So please subscribe the channel and fill the Google form to join the group given in the description. Which elementary row operations we are applying? We are going to apply 3 row operations. First is replacement. Replace one row by the sum of itself and the multiple of other row. That means Ri plus K times Rj. That means replace this Ri row by sum of this Ri plus K multiple of other row Rj. This is the replacement operation. Ri plus Krj is a replacement operation which replaces Ri. Second, interchange. Interchange any 2 rows. That means interchange ith row with jth row. Change the places of ith and jth row. Ith row shall be placed at jth row's place and jth rows can be placed at ith row. Third, scaling. Scaling means multiply all the entries in a row by non-zero constant. This is the third operation. That is denoted by K times Ri. That means multiply all the entries in a row by a non-zero constant. Row operations can be applied to any matrix, not merely to one that arises in the augmented matrix of a linear system. It can be applied anywhere. The following matrices are in reduced echelon form. The following matrices are in reduced echelon form because the leading entries are 1 and there are zeros below and above each leading one. 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1 and 0, 0, 0, 1, 0. This matrix is in reduced row echelon form. That means this row is non-zero, this row is non-zero, this row is non-zero and this row is non-zero. All non-zero rows has a leading entry 1 and the leading entry of the lower row is to the right hand side of the leading entry of the upper row. This is the leading entry of lower row, second row, and this is leading entry of the upper row, first row. See, leading entry of second row is to the right of the leading entry of first row. Here, this is leading entry of third row. It is to the right of the, and here we have to keep 0, 1. And see, this leading entry of the lower row, fourth row, is to the right of the leading entry of the upper row, that is third row. And if there is one more row called as 0 row, then it is at the bottom. 0 row, that means row containing all zeros, must be at the bottom of the matrix. Then this is the reduced row echelon form of the matrix. Any non-zero matrix may be row reduced, that is a transform by elementary row operations, into more than one matrix in echelon form using different sequences of row operations. However, the reduced echelon form 1 obtained from the matrix is unique. Theorem: uniqueness of the reduced echelon. Each matrix is row equivalent to one and only one reduced echelon matrix. This is the uniqueness theorem. Uniqueness of the reduced echelon form. The statement of the theorem is each matrix is row equivalent to one and only one reduced echelon form of the matrix. We shall prove the statement of this theorem. We shall prove this theorem in our next separate video. Note: if a matrix is a row equivalent to the echelon matrix U, we call U as a echelon form or reduced echelon form of A. If U is in reduced echelon form, we call U the reduced echelon form of A. Now we will define pivot positions. When row operations on a matrix produce an echelon form, further row operation to obtain the reduced echelon form do not change the position of the leading entries. Since the reduced echelon form is unique, the leading entries are always in the same position in any echelon form obtained from the given matrix. These leading entries correspond to the leading ones in the reduced echelon form. Now, definition of the pivot position is like this. A pivot position of a matrix in a matrix A is the location in A that correspond to the leading one in the reduced echelon form of A. For example, reduce the matrix A below to echelon form and locate the pivot columns of A. Before that, we shall see what is the pivot position. Suppose this is a matrix. In this matrix, the pivot position of this row, this is the pivot position, that is leading one, leading entry is 1, and this first column is called as pivot column, and pivot position is A11, first row, first column. This is the pivot position of this matrix, of this element. Then pivot position of this element, this is the pivot element, and pivot position of this element is A23, and third column is a pivot column, and this is the pivot position of this element, which is first non-zero entry, and its pivot position is A34, and this is the pivot column. Thus we can easily judge pivot position of the element and pivot column. Now we shall see example. Reduce the matrix A below to echelon form and locate the pivot columns of A. We have to reduce it to the echelon form. Here this is the matrix, and we know that the first element here must be non-zero. For that we shall transfer this, we shall use the operation R14. We shall interchange fourth row and first row. Therefore we will get fourth row become in first position 1 4 5 minus 9 minus 7. Then second row and third row will be as it is, minus 1 minus 2 minus 1 3 1. Then third row is also as it is, minus 2 minus 3 0 0 3 and minus 1, and first column row becomes fourth row, 0 minus 3 minus 6 4 and 9. Thus we have interchange first and fourth row, and matrix becomes like this. Now in this matrix I want to make these elements below 1 as a 0. This fourth row is a 0, but in second row there is minus 1, in third row there is minus 2. To make this minus 1 0, I shall use R2 plus R1. In R2 I shall add R1, and to make this 0 I shall use the operation R3 plus 2 times R1. I shall use that lead of pivot 1 to make these entries 0. row will remain as it is, 1, 4, 5, -9, -7. Then second row, in second row we have to add the elements of first row. -1 plus 1, 0. -2 plus 4 plus 2. -1 plus 5, 4. 3 minus 9 minus 6. 1 minus 7 minus 6. For third row, I shall add 2 times first row. -2 plus 2, 0. -3 plus 8. 2 times 4, that is 8. -3 plus 8 is -5. -2 plus 2, 0. -3 plus 8, that is 5. 0 plus 2 times 5, 10. Then 3 plus 2 times -9, म्हणजे 3 minus 18 minus 15. And -1 plus 2 times -7, that is -1 minus 14 minus 15. And fourth row will remain as it is, 0, -3, -6, 4 and 9. Thus we made first entry 1. Now what is our next job? We have to make this second leading element 1. How we can make this element 1? Divide second row by 2, that is 1 by 2 R2. 1 by 2 R2. This operation we shall use on this matrix. First row will remain as it is. Then second, to the element of second row we have to divide by 2. 0, 2 by 2, 1, 4 by 2, 2, -6 by 2, -3, -6 by 2, -3. And third row will remain as it is. Fourth row will also remain as it is. Now what's next? Next we have to make this element 0 by using this one. We have to make these two elements 0. Therefore first row remain as it is. Second row will also remain as it is. 0, 1, 2, -3 and -3. For third row we are subtracting 5 times second row, that is R3. We are using R3 minus 5 times R2. And for fourth row we are adding 3 times R2, R4 plus 4 times. We are using this leading one only to make the element 0. 0 minus 5 times 0, 0. 5 minus 5 times 1, 0. 10 minus 5 times 2, 0. -15 minus 5 times -3, that is -15 plus 15, 0. And -15 plus 15 again, 0. Now make this element 0, that is R4 plus 3 times this, minus 0 plus 3, 4 times 0, not 4 times, 3 times. -3 plus 3 times 1, 0. -6 plus 3 times 2, -6, 0. 4 plus 3 times minus 3, that becomes 4 minus 9 is equal to minus 5, and 9 plus 3 times 9 plus 3 times minus 3, that is again 9 minus 9, 0. This is a non-zero row and this is a row 0 row. What is our rule? Our rule is to replace the 0 row at the bottom. Therefore, I shall make use of R3, 4. 1, 4, 5, minus 9, minus 7, 0, 1, 2, minus 3, minus 3. Then fourth row I shall place at third row. 0, 0, 0, 5, 0, and fourth row becomes 0, 0, 0, 0. Now I have to make this element 1. For that purpose I shall use the row operation 1 by 5 R3, and if I use 1 by 5 R3, see what happens. First row becomes as it is, second row as it is, fourth row as it is, and this for this third row I have to divide. Therefore this 5 becomes 5 by 5, 1. This is the matrix in echelon form, and the leading entry is 1. This is the first pivot position, this is second pivot position, and this is third pivot position. The first pivot position is at place A11. Second pivot position is at place A22. And third pivot position is at place 34, A34. And first column is pivot column, second column is pivot column, and fourth column is pivot column. Dear friend, please subscribe the channel if you like the video, and don't forget to press bell icon so that you can get the updates of the channel. Thank you. See you in the next video.